In central Queensland, Australia, a machine larger than most buildings takes a step every few seconds and covers barely 8 feet with each one. It has no wheels and no tracks. Instead, it lifts its entire weight onto 2 massive steel shoes, shifts forward, and sets itself down again, advancing across the earth in a motion that looks less like machinery and more like something learning to walk for the first time. This is the Marion 8750, and when it was unveiled at the Callide Coal Mine in 1993, it was the largest dragline in the entire southern hemisphere. Queensland's Bowen and Callide coal basins were, by the early 1990s, among the most productive open-cut coal regions in the southern hemisphere, feeding both the domestic Australian power grid and a growing export market shipping coal to Japan, South Korea, and other industrial economies across Asia. Unlike the deep underground mining that had historically defined coal extraction in much of the world, Australia's coal basins were shallow enough and extensive enough to favor open-cut mining almost exclusively, stripping away overburden layer by layer rather than tunneling beneath it. That approach demanded exactly the kind of large-scale excavating equipment the American coal industry had spent decades refining. Australian mining companies did not need to invent this technology. They needed to import the largest, most proven version of it, and adapt it to a landscape and climate very different from the American Midwest. The arrival of the Marion 8750 at Callide in 1993 was a direct result of that demand. A mine that needed to remove enormous volumes of overburden as efficiently as anywhere on Earth, choosing a machine platform that had already proven itself in decades of American coal production. To understand why a machine needs to walk instead of drive, you first have to understand what it is being asked to do, and why every other option had already been ruled out. A dragline exists to remove overburden, the layer of rock and soil sitting on top of a coal seam, and move it somewhere else without physically driving material back and forth on wheels. The Marion 8750 does this with a bucket suspended from cables beneath a boom that can stretch past 360 feet, capable of holding anywhere from 100 to 152 cubic yards of material in a single pass, and lifting a suspended load of up to 760,000 pounds. None of that weight, none of that reach, sits on a wheel or a track. It sits on 2 enormous steel shoes, one on either side of the machine's circular base, and when the machine needs to move, those shoes do the work that wheels would do on almost any other piece of heavy equipment on Earth. The walking mechanism is not fast. Each step advances the machine roughly 2.4 meters, a little under 8 feet, and the entire process of lifting, shifting, and resetting the base happens in a slow, deliberate rhythm that can take minutes to complete a single stride. For a machine this size, that is not a flaw. It is the only way to move 8 million pounds of steel across ground, too soft, too uneven, and too actively being mined to support continuous wheels or tracks. A crawler-mounted machine of this scale would need to distribute its weight across a much larger footprint, or risk sinking into the same overburden it was built to remove. The walking shoes solve that problem by lifting the entire machine clear of the ground between steps, setting it down only when the next position has already been chosen. At the core of the 8750's design is a simple economic argument that most people outside the mining industry never see. Removing overburden with trucks means loading it, hauling it, and dumping it, a cycle that burns diesel fuel with every single trip and requires a driver for every single truck. A dragline eliminates almost all of that. It digs, swings, and casts the material directly into the space already mined out behind it, in one continuous motion, without a single truck ever entering the equation. The Marion 8750 runs entirely on electric power, drawing current through a heavy trailing cable rather than burning fuel on board, which lowers both its operating cost per ton and its emissions compared to almost any other method of moving the same volume of earth. The specific technology behind that electrical efficiency has itself evolved significantly since the 8750 was first introduced. Later and upgraded versions of the machine run on what is known as AC IGBT electrics, a drive system built around insulated gate bipolar transistors, solid-state components, capable of switching electrical current on and off thousands of times per second, with far greater precision than the older DC motor systems that powered earlier generations of draglines. This matters in a very practical way on a machine this size. Every time the dragline's drag or hoist motors changed speed or direction, older systems lost a meaningful amount of energy as heat, simply because of how DC motors have to be electrically managed. An AC IGBT system controls that same motion with far less wasted energy, which translates directly into lower electricity costs and less heat that has to be managed inside the machine's electrical house, particularly important in the sustained tropical heat of central Queensland. It also allows for faster, smoother cycle times, meaning the bucket can complete its dig, swing, and dump cycle more quickly without subjecting the machine's structure to the kind of abrupt mechanical shock that shortens the working life of gears, cables, and structural steel. None of this is visible from outside the machine. It lives entirely inside the electrical house, in cabinets of solid-state components that most people who watch a dragline work will never see. But it is the reason a machine using this much power can run, essentially continuously, for decades, without the electrical system itself becoming the weak point in the operation. At the scale of a mine producing millions of tons of coal a year, that difference in cost per ton compounds into a genuinely different economic model for how the mine operates. Running a machine like this is not a job that fits neatly into a normal work schedule. At Callide, the dragline crew works 12-hour shifts, around the clock, 7 days a week, because a machine this expensive to build and this central to the mine's production does not stop simply because the sun goes down. Operators rotate through the cab, through time spent on the dozer, working the immediate area around the dragline, and through routine inspection of the machine itself, walking its structure by hand to check for the kind of wear that has to be caught early on a machine operating at this scale. Running the controls well enough to keep the bucket, the swing, and the walking cycle working together smoothly is not considered a transferable skill from other heavy equipment. Within the industry, the operators who can do it are known, half jokingly and half with real respect, as swing kings, because the coordination required has almost nothing in common with driving a truck or running a standard excavator. That coordination has to account for far more than just moving the bucket efficiently. A dragline operator is constantly managing the relationship between 3 separate motions happening at once: the drag rope pulling the bucket across the ground, the hoist rope controlling its height, and the swing motion rotating the entire upper structure toward the dump point. Get the timing wrong, and the bucket can strike the boom on the way past, or arrive at the dump point still swinging with enough momentum to damage the structure it is unloading onto. Experienced operators learn to feel this relationship rather than calculate it consciously, adjusting the 3 motions together in a way that keeps the bucket's path smooth through an entire cycle that might repeat, without pause, for the full length of a 12-hour shift. Outside the cab, the inspection routine is just as demanding. A structure this large, built from welded steel and subjected to constant mechanical stress, cannot rely on scheduled major overhauls alone. Crews walk the machine's walkways and structural members by hand, checking for the early signs of fatigue, cracking, worn pins, and stretched cable that, left unaddressed, could eventually take the machine out of production for weeks rather than hours. On a piece of equipment this central to a mine's daily output, catching a problem during a routine walk-around inspection instead of during an unplanned breakdown is not a minor operational preference. It is often the difference between a mine hitting its production targets for the month and falling meaningfully behind them. The 8750 is not a single, unrepeated machine the way some of the largest shovels in mining history were. It is a model, built and rebuilt at different mines across multiple decades, with configurations tailored to each site's own geology and production targets. That is, in its own way, part of what makes it remarkable. It was not built once as a spectacle. It was built as a working answer to a problem every large open-cut coal mine eventually faces. How do you move an enormous, continuous volume of earth indefinitely at a cost the mine can actually sustain? Marion Power Shovel, the company that originally designed the 8750, had been building walking draglines since 1939. Working out of Marion, Ohio, the same town its largest shovels would later make famous. The company built its reputation on machines that broke size records decade after decade, culminating in shovels large enough to be measured in stories rather than feet. But by the time the 8750 was designed, the industry's needs had shifted. The era of building single, unrepeatable giants for record books was giving way to something more practical, a reliable, electrically driven dragline platform that could be built again and again, at whatever scale a given mine actually required. Marion itself did not survive as an independent company much longer. It was acquired by Bucyrus International in 1997, which was itself acquired by Caterpillar in 2011. The 8750 outlived the company that invented it, continuing in production under new ownership because the underlying engineering still solved the same problem it always had. At Callide, the machine that walked onto the site in 1993 as the largest dragline in the Southern Hemisphere is still doing exactly what it was built to do, taking a slow, deliberate step every few seconds, swinging a bucket the size of a small room and quietly moving more earth per dollar than almost any alternative the mining industry has ever built. It does not look impressive the way a fast machine looks impressive. It looks impressive the way something enormous and patient looks impressive, doing the same motion, correctly, for decades, while the ground beneath it changes shape one step at a time,